This is exercise 14a and this is question 1. Prove that the moment of inertia of a uniform rod of mass m and length 2l about an axis through an endpoint perpendicular to its length is 4/3 ml squared. Now, the thing to remember about the rod is, okay, if we make our rod here, red line is the rod, we make this rod here, the axis, previously we did one that goes through the middle, and if it goes through the middle, okay, what it is it basically causes it to rotate around in this direction here, because the axis is actually going through this point. So it's basically like this, and it's causing my hand to rotate. You understand? That's the rotation that's involved in this question, okay? Now, we no longer have the axis at the front, we have it at the end. Okay, so we're going to go through the exact same proof as last time, more or less, but with just one or two different variations on the answer. Okay, so there's going to be a length of 2l from here to here. Okay, so that's going to be 2l. 2l. Okay. Next thing you got to know about the rod is that so it's a laminate or a rod? It's a rod. Okay. Now the rod is basically, we're going to do what we did last time. We're going to cut out a small part, delta x. Delta x eventually turns into dx, as it would once you integrate it. Okay, and then it's a distance x away from the rotational axis, which is here. This is the rotational axis. Okay, so we're going to do what we always do. We're going to find out what rho is. Let rho be the mass per unit length. Yeah. But this means it's the mass of the full rod divided by the length of the full rod. This means mass equals 2 rho L. Have you enough of that? Okay. The next one is, then we have to figure out what m is, okay? And, okay, delta m equals rho delta x. Isn't that right? The change in mass equals the change in equals the mass per unit length multiplied by the length you have of that small piece. Okay. So if I change this into integration terms, it looks like this. Do you know, where you change summation to integration, that's what you'll have. Okay. Next part after that is basically how do we find out what I is, okay? Now what is I again? I was the sum of delta m x squared, wasn't it? Okay? And what we can say then is I is the sum of, what's it? I'm going to change it into integration in a second, right? So it's going to be p x squared delta x, and that's the same thing as the sum of the integral of p x squared dx. Okay? So just p x squared dx. Okay? Now, what you could remember off by heart, and you'd be well in your reason to learn this off by heart, is you could just learn this. It's the same thing. You don't have to go through the same rigmarole all the time. You can just learn something like this and then integrate both sides. Okay? So when you integrate both sides, what you're going to get is I equals the integral of x squared dm, and then you just simply change your dm into rho dx and you get the same thing. You can just, that's a shorthand way of doing it. I've done it ridiculously formal here. But you don't have to do a formula every time. You can just learn the red box and learn to jump in there and then substitute dm with rho dx. It's the same thing. Alright, now that we're at this stage, we have to find out our limits, okay? Now, unlike the last question where we had L and minus L, remember we had L and minus L because it's in the center. This time we have it at the end, so it's just going to be 2L and 0. And then when we integrate, we're going to get a third x cubed, a third rho x cubed from, that's not an e, that's a rho, that didn't help it any, equals a third rho x cubed 2l to 0, And now to figure out how this works, okay, so we're going to end up with I equals 1, it's going to be 8 rho L cubed over 3. Just sub in 2L cubed for x, and you'll get 8L cubed, okay? 8L cubed divided by 3. Now we're not looking to prove that. We want it to be, what do we want it to be? We want it to be 4 over 3 ml squared, okay? So to sort this out, what we need to do is we need to take out 4 over 3 on its own, okay? So we're going to take out 4 over 3, and then we're going to take out L squared at the end, and in the middle that will leave me 2 rho L. 2 rho L is M. M is 2 rho L. So it's 4 over 3 ml squared. You happy enough with that? Okay. The next one I'm going to try is, I'll do question 3, which is now, okay, question 3. Are we happy with that? Any questions? Okay. The next thing we're asked in part 2 is to find the radius of gyration, okay? Now the radius of gyration of a body about the axis, okay? The formula is I equals mk squared, okay, where m is the mass, k is a fixed distance from its axis of rotation, okay? So we have to find out k is the radius of gyration, okay? So we're imagining the full system as one big mass. So it has to have the same inertia as the answer we just found, okay? So I is 4 ml squared over 3. M is still M, K squared is still K squared. So the M's will cancel. And what we'll find out is K is going to be the square root of 4L squared over 3. Or if you really want to break that down, technically speaking, it's going to be 2L over root 3. Because 4L squared is 2L by 2L. 2L by 2L. Okay, is 4L squared. So that's where we get that from. Okay, try number 3. Question 3. Okay, question 3 is a uniform annulus, which is basically it's like a disc, but it's missing part of it. So basically, it's exactly like a CD. Okay, so here's our uniform annulus here. Okay, and 1 second. Okay. Okay, so there it is there. Now, consists of a disc radius 3 meters with a disc of 1 meter, a radius 1 meters removed. So what we're going to do here is we're going to have our center to here is going to be 3, and our center to here is going to be 1. So we have 1 and 3 respectively. 1 and 3. Okay. The mass of the annulus is m, so the full thing has a mass of m. Prove that the moment of inertia of the annulus about an axis through its centre, perpendicular to its plane, is 5m. We want to prove that I is 5m, and it's exactly the same as the proof. It's going through it. Okay, so if you imagine, if I was to draw a 3D version of this, okay, what we're looking to do is we're looking at this type of rotation. This is the rotation we're looking at. Do you understand? So that's the sort of rotation we're looking at there. Okay, and this is the axis. Okay, so that's the rotation we're looking at here. Okay, it says keyword is what's the keyword? An axis through its centre, perpendicular to its plane. It's got to be perpendicular to the entire plane of the disc. Okay, so that's that one done. Okay. Now, if you're talking about planes that are perpendicular to each other but horizontal to the disc, you'd be talking about these ones here. Sort of like an XY axis, okay? Now that's dealt with, okay? The next thing we're going to do is we're going to figure out how we're actually going to go about doing this, okay? Once again, like our formal proof, we're going to define rho as mass over area. Okay? Now, what is the area of this? It's the area of the big circle minus the area of the small circle. So it's going to be pi times 3 squared minus pi times 1 squared is its area. Therefore its area is going to be 8 pi squared. 8 pi even. Yeah, 8 pi, and its mass is still m. This means that m equals 8 pi rho. Okay? Okay, I'll just make this smaller, and now we can move on to the next part of the question there. Okay, now the next part of the question is we got to do our usual integration part. Okay, so the whole goal of this question is to find out what I is. Okay, now remember what we said earlier. You can learn off by heart that di is r squared dm. It's basically the length squared times the integration of mass. You can learn that off by heart. It's the same thing as going through our formal proof. Okay. Now this is defined as radius. Now, what's going to happen here is okay. So what we're going to do is we're first going to express dm in terms of p and dA. Okay, so dm is rho times dA. Okay, and our variable is the radius. If our variable is the radius, okay, we got to make sure that the dA turns into dr. That's why we can't use dm. We can't use dm because mass isn't the variable. Radius is the variable we need to use, okay? So we need to find how to change this into the radius, okay? Now, what is dA equal to? Or the change in volume? So if you're to cut out a little, I'll show you now. If you're to cut out a little circle from this, something like this. I'm just cutting out this part out, okay? I'm going to draw this bigger. Now remember the formal proof, okay? When I draw this much bigger, I'm just cutting out a small section, okay? Now the small section is dm, okay? But we have to figure out what is its area. So this is going to be dr, just a small distance, okay? This is dr. So remember what we said, when you cut this in half, what happens? It turns into a, anybody? Nearly a line. The big thin rectangle, right? And the big thin rectangle is of dr in width. And what is its length? Can anybody tell me? Its length? It's the radius away, which makes it 2 pi r. Right? Now why doesn't, I told you this earlier, why, you know that the outside line is going to be bigger than 2 pi r, right? Why doesn't it make a difference in this question? So narrow, so small that both of them are practically 2 pi r. It's tiny, you can't even see it. Okay? Now, that's done there, okay? What we're going to do is figure out what dA is. And dA is dm equals rho times dA, which is rho times 2 pi r dr. Okay? Now, if we're to integrate our box, what we'll always get is, you can almost, I is the integral of r squared dm. Okay? Now, what we got to do is we got to figure out how to change r into the variable. So I therefore is going to be the integral of what is that? 1 0 you say. 3 1. I'll explain now why it's 3 1. Do you remember? It starts at, see the way 1 is when it starts. See? It starts at 1 and ends at 3. So it's the integral from 3 to 1. 3 to 1, 3 to 1. Because there's no mass below 1, so it can't be 0 to 3. Okay? R squared dm gets changed into 2 rho pi r and r squared makes r cubed dr. Integrate. And when we integrate, we're going to get what's it going to be? A quarter 2 pi r to the power 4 3 to 1. Now what I can do here is I can just quickly rub out the 2 and turn that into a half. Okay. Now there is one thing here that I've got to watch out for as well. When I do all this, okay, I really could have changed okay, just trying to figure out how I get rid of the row. What's m equal to? M is 8, see that? M is 8 pi row. So I'll see if I can sort that out. I'll do it at the end. Okay, so we'll put it in and we'll get, what's 3 to the power 4? 81 over 2 pi row. Then 1 there is going to be minus a half pi row. So what's that going to get me? 40 pi row. And what did we say for? It's 8, isn't it? M equals 8 pi row from earlier. That goes in 5 times, so it's 5m. There, okay? I'm going to go down and